This is version A of the data analysis pre-release questions for 2017. In exactly the same way as in the datasheet and in the actual exam, these will be done in the same order. So you'll see it corresponds section A, vehicle registrations, and this will be the first bit that we look at. So, describing the trend in vehicle registrations from 2002 to 2006. Looking at the graph we are working on, we've got 2002, which would be this one, and we've got 2006, which would be this one. So if we look at the trend over this time frame, we can see that it is decreasing. So it's going down over this time period. So this can be simply answered as the trend is decreasing. Calculate the number of vehicles registered in the third quarter of 2014. So 2014 is going to be our important piece of information. If we look on the original datasheet, we are told that it was 8% up on the same quarter of 2014. We are also told the number of vehicles in 2015. So from this, we're going to be dealing with 2014 and 2015. The old one is always going to be the 100%, and then we had an increase up to 108%. So using the original information, we can take the number of cars in 2015 and divide it by 1.8, and that is a percentage multiplier. So we are dividing by this 1.08 because we are going back in time. If we were going forward in time, we would multiply. And this gives us a value of 811,111. So we can have that to three significant figures, or 111,000. Okay, so on part C, we've got a diagram of new registrations in Great Britain. So we are asked to calculate the number of cars specifically in 2015. So using our information again, the cars is this section at 81.3%. And the total number, which we used before, is your 876,000 vehicles. So we know that our cars is the 81%. So our total number of vehicles times by 81.3% will give us the total number of cars. Okay, so we are looking at the number of cars still, and that are registered by the end of the second quarter of 2015. So we're dealing with three different timeframes. We're dealing with the end of the second quarter, what happens in the third quarter, and then the end of the third quarter. So we know from C part 1 the number of cars registered during the third quarter. We know from our data sheet that there were 30.2 million cars registered by the end of September, and end of September is the end of the third quarter. So, end of the second quarter, you would then add this to get here. So, if we convert this into millions as well, we end up with a final answer of 29.5 million, and that's at the end of the second quarter, beginning of the third quarter. So calculate percentage change. So percentage change is always going to be the change divided by the original value or the earliest value. So in this case, we are going to need to divide by the end of the second quarter because that comes before the end of the third quarter. So the change in number of cars is going to be something we've already used. So the change in the number of cars is going to be this value here, the value we found in part 1, and we are going to be dividing that by the 29.5 million, so the original value, and then times by 100 to turn it into a percentage. So we are looking at a 2.41% increase. The second section is talking about the UK Snooker Championships, which can be found on page 3 of our datasheet. It asks us to calculate the mean and the standard deviation. So this is a case of putting it into your calculator, and these can go into list 1, and then you can look up on the calculator your mean and your standard deviation. You should hopefully get a mean of 45.5 and a standard deviation of 32.9. And then we are asked to compare. So compare the values that we've just got and the values from Neil that we can find in our datasheet. And we are asked to do that in context. So we know that the mean and the standard deviation is 59.7 and 39.2. So when we compare it, we've got Neil's is a higher mean, so this suggests that he scored more points each frame, and Neil has a higher standard deviation, and this means that his scores were less consistent. Section C is the predator-prey relationship on page 4 of the datasheet. On our original datasheet, we were given details from 1875 down to 1903. However, the question that we are dealing with here isn't asking for all of that. It tells us what the correlation coefficient is in the first time frame and asks us to calculate it for this second time frame. So 10 years later. So putting those into our calculator, we're going to be using two variables. So they need to be set up for that. And then we've got a new correlation coefficient. The correlation coefficient is R. So what we've ended up with is for 3A, our correlation coefficient should be 0.912. Now we are then asked to compare the correlation in context. So we're not just looking at whether it's strong or weak, or whether it's a linear relationship or not. We're asked to do it in context. So, although they're very similar, the first one here is slightly larger, and so the linear relationship at this time is slightly stronger. So in 1903, because we've ended up as 91.2, it's a slightly less strong correlation. So this is going to suggest that the linear relationship between the links and hair is better in the original time frame we were given. And we can refer to the population because it tells us at the bottom that these numbers are proportional to the two populations over this time period. Okay, so for part C, we are using the data between 1885 and 1904, and we are being asked to get the equation of the regression line. So this is going to be under reg on your calculator, and it's going to be in the form y equals mx plus c, because we already know it's a strong linear equation. So we should have an answer that comes in at y equals 0.405x plus 13.2. So for the gradient, so we've got the gradient in context. So the gradient is going to tell us that each time our value of x increases by 1, our value of y is going to increase by this gradient. So in context, it's suggesting that as the number of hairs increases by 1,000, because this is both being measured in thousands, that the number of the links will increase by 0.405 of 1,000, which is 405. So then we are using our equation to predict the links in a year when there were 120,000 hair. Now again, 120,000 hair, we are measuring it in thousands, so that's going to be 120. So first off, we know that x is 120, so we can substitute our 120 into our equation, and we should get an answer of 61.8. Now because this is 1,000, it's not a problem because it's not a part of a links. It's effectively 800 links. Okay, then we're asked to predict. So we're predicting the number of hair when there were 9,000 links. Sorry, 90,000 links. So we are going to have to be using links this time, which is our y. So we're looking at 90y. We can substitute this 90 into our equation and rearrange it to get a value for x. So to 3 significant figures, we're looking at 190,000 hair. So, comment on your reliability. Which is more reliable? There are 2 things that make something unreliable. When it has weak correlation, so a value of r that is almost 0, or when it's outside of the data set. So if we look at our data set, then for our hairs we were asked about 120,000, and this one goes up to 137, so that one's fine. And we were asked about 90,000 links, but this only goes up to 80. So it's going to be our 90,000 links that are less reliable because this is outside of our data set. So it's outside of our data range. Fetal growth. The data sheet for this bit is not actually massively useful. The closest bit we've got is the fact that it refers to percentiles, so we're likely to have to know how to convert percentages into decimals. So, first off, we are dealing with a 16-week-old fetus in this first section, and we are assuming it has a mean and a standard deviation. Then we're asked to calculate, and we're asked to do this as a percentage that would have a weight of less than 150 grams. So actually at this point we've got all of our key information. So writing this down, we've got a mean, we've got our standard deviation, and we have our number in context, and it's a less than. So the probability that the value of x is less than or equal to our number in context is the first line that we're going to need to write down. We're then going to need to calculate z, and this is going to be using the equation of x minus mu over sigma, which is one that we just have to learn. Once we've got z, we can put this in and then either use a calculator or read it off tables. But we're asked for a percentage, so we're going to have to times it by 100 to convert it into a percentage. Okay, in our second question, we have a weight that is more than 170, but because we're still dealing with the 16-week fetus, we can still use the same information from above. So exactly the same way, mean, standard deviation, 170 and more than. So probability that x is more than 170 is going to be the probability that z is more than, using our z equation of x minus mu over sigma, which comes in at 1.23.
when we get our probability out, it comes up at 0.1, which is less than a half. So this means that we're going to have to use 1 minus, flip the sign so it's less than, and again they asked us for a percentage, so we are going to need to convert that into a percentage. Okay, part 3, if its weight is in the top 10%, we're still dealing with a 16-week gestation. So this time, instead of having a value of x, we've been given a value for the probability. Still 16 weeks, so the information is still going to hold. So we've got our mean, we've got our standard deviation, and we've got our probability, and we know that it is less than because it's in the top 10%. So top 10% is going to be 90% below, 10% above. This is going to be an inverse type question. So if you work this out on your calculator, it will give you a value straight off for x is 171 grams. We are still going to have to use the z equation and find out what z is, and then rewrite our z equation to be able to find out officially what x is. So in reality, using the inverse on the calculator, you can find out what x is straight away. However, we do still need to use the z calculation to find out what z is. Part B is a little bit harder. So we're still dealing with a large fetus, so in the top 10%, but this time we are dealing with 40 weeks. This time we have a mean that's quite a lot higher, which is what you'd expect because the fetus is quite a lot older. So calculate the value of the standard deviation, so that's what we're going to need to find out. So that the smallest large fetus was this. So that's going to give us effectively our upper bound. So information that we know. We know what our mean is. We know what our standard deviation is. We know that our probability is 0.9. Now, and we know what our number in context is. It's the 4234, which was given to us at the bottom of the question. Okay, that's probably the best way of showing it. So, at the moment, we've got these top bits of information. Now, your calculator, if you do this as an inverse, you can ask it to find out what z is. If you use a mean of 0, a standard deviation of 1 and a probability of 0.9, it will calculate you a z value. From there, you can use the equation that we used for calculating z. So z is x minus mu over sigma. And once we've got that, then we can rearrange it. So from there, when we rearrange it, we will end up with this one, which should have a line in the middle because it's a fraction. So rearranging to get this,
you're not going to need this line particularly.
So you've got a standard deviation of 480 to 3 significant figures.